All right, we're going to do a continuation of our torsion. Last time we talked about torsional shear stress, and today we're going to add on angle of twist. So we are limiting our discussion to round or circular cross-section shafts. They could be solid or they could be hollow, but we're not doing prismatic shapes. Those would be a little bit different than, same idea would apply, but the corners that would be at the cross sections, whether they're right angles or 60-degree angles or whatever they might be, they would create a little bit different approach, particularly on calculating their polar moment of inertia, and there would be some stress concentration. So we're only doing round circular shafts. Let's go over here and define some variables. So today's new idea is angle of twist. It's going to be theta, and if we were looking, well, let's just draw a shaft, label stuff, catch up from last time, and let's do this one sort of in isometric. I wonder if I can do this. Yeah, okay, good. And then maybe we can well, I didn't want to do that. Maybe, all right, so I should do it this way. Nope, not like that. Let's have two of these guys. Something like that, and let's say that we're looking at it this way. Okay, so here's our stubby little shaft. Let's put a torque on it. We will need that in order to make it do something. Last time we had mounted the other end to like a wall or whatever. This time let's just show the opposing torque as what it keeps it in equilibrium. We also have the idea that we might need to know the length, and that's just going to be L. Now if we were to draw, let's draw this color. If we were to draw a line across here on our shaft before we apply the torque, and then we apply the torque, and there's a sufficient torque to actually make the shaft twist, then that line would go from point, let's call it AA, to, it would do something like this. I'm exaggerating it, but we'll call that A to A prime. So point A on the shaft would move up to what I have labeled point A prime, or down, depending on which way you were twisting it. The way I drew the torque, it would twist it upwards. And, that's if we had physically gone and drawn a line on the outside of the shaft and twisted it, that line would do something like what I've created here. The angle of twist is related to that amount of rotation. Not rotation, just twisting. So if we were to look at the end of this thing, something like that, here's the center of the shaft. Now we're looking at a end view of it. And here would have been point A to start with, and then maybe over here is where A prime ended up at. So our angle of twist is this angle right there. So theta is what we're calling the angle of twist. And when we calculate it, we'll show you the equation in a second. When we calculate angle of twist, it will produce units of radians. All right. So a lot of times we'll have to convert over to degrees because we more often talk about angles in degrees instead of in radians. But that is what the equation will give us. So the actual equation is theta equals T, so the internal torque for whatever section we're talking about, times L, the length of that section. So here I've got L as the whole shaft because we've only got one torque applied to it. It looks like two torques, but there's one torque and the reaction to that torque. So TL over J, which is the polar moment of inertia. We talked about that last time. So remember, we had a couple of things that it could be. So the actual equation for polar moment of inertia would be the integral of rho squared dA. But instead of integrating the cross-section every time with this equation, what we do is, first of all, we limit our calculations to circular shafts, so shafts that have circular cross-sections, and then evaluate that circular cross-section in this integral of rho squared dA, and we get either pi over 2 times c to the fourth minus b to the fourth, where c is the outer radius and b is the inner radius. That's a semicolon, not a j. C equals outer radius, and b is inner radius. Sometimes the shaft is solid and b is 0, and that just makes the equation a little bit easier. We actually were using more often pi over 32 times d to the fourth minus lowercase d to the fourth. So this is if I wanted to use diameters. And the same thing where a solid shaft, the inner diameter would be 0. The pi over 32 version is usually a little more convenient because, again, when you're measuring diameters or measuring a shaft of some kind, you're usually measuring diameters. You're not normally measuring radius. Or if you're talking about a shaft, you know, it's a 2-inch drive shaft or something, you aren't referring to the radius. So usually when you're talking about these, measuring these things, fabricating these things, you're dealing with the diameter. But you could calculate either way. You could calculate using the radius or the diameter, but a lot of times it's just simpler to stick with the diameter. But you do have to change your equation to pi over 32 instead of pi over 2. Let's see. One more part of our equation. TL over JG. We have not used G very much, if any, at all. G is the modulus of rigidity, also called the shear modulus. I think your book, when you look up material properties, it uses modulus of rigidity. So it's similar to modulus of elasticity, capital E, that we have been using several times, but it's related to shear instead of axial type stresses. And so it's the same type of thing, material property, it's just related to shear. And you can look it up in a chart somewhere, just like you would look up modulus of elasticity. Now, this equation, this is the equation we would use. It looks pretty familiar, so it's easy if you can remember the axial deformation equation, because this is very parallel to that. The same kind of thing, except instead of stretching or compressing and changing shape, it is twisting and changing shape. But remember the axial deformation equation, just so we have that. Delta equals FL over AE, or EA, but it doesn't matter, it's multiplication, so it doesn't matter, but I'm putting it in the same order as I just wrote the TL over JG equation, where you've got some kind of force in the axial deformation, it's an axial force. In the angle of twist, it's a torque. Then you've got the length of, and that's the same in both cases, it's the length of the section where that force or torque is applied. Then it's got something to do with the cross-section. In delta, it is the cross-sectional area. In theta, it is the polar moment of inertia for the cross-section. And then it's got a material property. So they're very similar types of equations, and you use them in similar ways. All the kind of stuff that you did with delta, you'd have to do with theta. You know, where you Do it section by section if you have multiple forces or multiple materials or multiple sizes of cross sections. Then you have to, each little section has to have all of these variables TL, J, and G constant in that section, and then you can calculate theta. And then you define a new section with a new set of TL, J, and G's for just for that section, and you can calculate theta there. So it's very similar to the way delta works. Let's look at web work and see if we can find us a problem to work. Let's see. Oh yeah, I'd already pulled this one up. Let's just do this one. This one will let us go back and do some of the stuff from last time and some of the angle of twist. So this is a good problem. Let me chop it out of here so that we can paste it into OneNote. All right. This one doesn't have a picture in it, and a lot of times you'll have these torsion problems with no picture because the picture is just a solid rod or a hollow rod, something like that. This one's hollow, so we haven't done a hollow one, at least not in the stream. Oh, that reminds me, on the web work, all of the web work, every bit of it, all the way back to homework 1, is currently open and set set to close August 11th, I believe. So the end of the quarter. So if you miss some stuff, you have a chance to go back and finish it up. Exam 3 does cover all the way back to the beginning, so you can go back and do all of the stuff if you want to. Practice it, do the optional problems, whatever. It's all open. Alright, so this one's hollow shaft, annealed titanium alloy. So that's a different material. We'll have to look at that material property. It has an outer diameter of 145 millimeters, at least for me. And ID inside diameter 97 millimeters. It has a torque, just a single torque. We're going to figure out shear stress on the inside and outside, magnitude of angle of twist, and then if it, and part D is interesting, the magnitude of the angle of twist in a same length section that has the same weight as the hollow one. So we take the hollow mass, shrink it down to a solid, and figure out what that angle of twist would be. That's interesting because it'll show us something about why you might sometimes want to have a solid shaft versus having a hollow shaft. So that's interesting. It's not asking us to do the shear stress any differently, but it is asking us to do the angle of twist differently. All right. I suppose we can draw a picture of this thing just to have it. We don't really need one, but let's go ahead and draw one. Let's just draw a side view, which is just going to be a rectangle. Didn't want to do it that way, though. Oh, but I wanted it to... There. All right, that's what I wanted. So, but it is hollow, so let's draw us a some dotted lines here showing that it's hollow. Okay. It has a torque of what was it? 22.5 kilonewton meters. And we'll just show this end as having the opposing torque. I don't know what it's attached to, so I'm just going to show that it somewhere has a reaction torque so that it's in equilibrium. We have some dimensions about the diameters and the length. So we'll just do the diameters this way. Let's do them this way here. There's the outer diameter. Normally you show diameters on a circular, like if I had drawn the end view and had circles, the diameters would be labeled on that instead of the side view, but I'm not going to draw the circular piece, I think. So this is 145 millimeters. And then we'll do our inner diameter this way. Again, not the right way to do it, but it'll get the job done for now. 97 millimeters. We have our material is annealed titanium alloy. We'll need that when we go to do angle of twist. And we have the length of the thing. I guess we can put that on here. It was 3.1 meters. Okay. And let's just do the first one. The first two are actually talking about stuff we did last time. So torsional shear stress. That equation, tau equals T times rho over J. So the torque, if we want to do this completely thoroughly, then we could, you know, come here, cut the shaft open in the center of this section, and figure out that, oh, the internal torque is also 22.5 kilonewton meters, and go from there. Rho, now part A is different from part B in that one of them wants to know the shear stress on the outer surface, so the outer radius, and the part B wants to know the shear stress on the inner radius, inner surface. So that will be different values of rho. So my outer diameter is 145 millimeters. I'm going to divide that over to meters, and then I'm going to divide by 2, and I get 0.0725 meters as the outer radius. And then J will be pi, I'll use the diameters here, pi over 32. It is hollow, so that's going to be c to the fourth, which is 0.145 meters to the fourth, minus b to the fourth, which is the inner radius or diameter. I guess b technically is the radius and lowercase d is the diameter. 0.097 meters to the fourth. And need to make sure I'm not doing meters to the fourth. I'm raising that whole number to the fourth. Like that. Let's see. 0.145 to the fourth minus 0.097 to the fourth times pi divided by 32. So our, I guess I did it backwards, the denominator is 0.40 and 347 meters to the fourth. And the numerator, 22.5, that's kilonewtons, so times 1,000, times 0.0725. 1,600, 31.25, those units would be kilonewton meter squared. And then when I, oh no, that Newton meter squared. And then meters squared would cancel out with meters to the fourth to leave meters squared, and I'd have newtons per meter squared, which is a Pascal. So 1631 divided by my little denominator here is 47.01, I guess, megapascals, millions of pascals. So 47,010,086 newtons per meter squared, 47.01 megapascals. Let's go over to our web work and see if it likes that number. 47.01. It does like that, so good. Oh, where's I not? Uh-oh, no. Where did my... I may not have shown this. I can't tell which one was up. So you might have heard me say all of this without seeing it. You might have had to follow along on your own piece of paper. But here's what the work was for our problem that I was working on. Just if you want to review any of that. This one is, we're about to do the exact same thing again, but for the inner radius, so you can follow along with that. This set of work over here is the part A. So let's do part B. Part B wants the exact same thing, but it wants to do the torsional shear stress on the inside surface of this hollow shaft. And it will be different because rho will be different. The distance from the center of the shaft to the inner surface is different from the distance to the center of the shaft to the outer surface. It's somewhat different. So it's going to be a little bit smaller stress, but it shouldn't be a lot smaller. So let's plug those numbers in and see what we get for part B. Tau equals T times rho over J. So same torque is applied to the cross section. This whole shaft, anywhere, I drew this little green squiggly line in the center of the shaft. Anywhere I draw that green squiggly line, I would cut it open, draw that little free body diagram. I didn't bother to do that on this particular one. And then I would see what the internal torque is at that cross section. And no matter where I draw that green line at, the inner torque is going to be 22.5 kilonewton meters. So no matter where I'm at. We'll do some where that's not true later on, but for this one that is true. All right, so the torque is the same, 22.5 kilonewton meters. Rho is different. The torque is the same, but the place that we're interested in calculating the shear stress is different. So maybe it would help if I did draw a little end view of our shaft here. Let's do that right here. So there's the outer diameter of our shaft, but it is hollow. So I don't know if I can get that kind of centered up better. Something like that. There's our inner radius. So when we did part A, we were picking some point on the surface. Doesn't have to be that particular one. It could be any of these points on the surface. They're all the same distance from the center. And that's what we were using for rho, is the distance from the center of the shaft out to point A. But now for part B here, we're calculating the shear stress somewhere on the inner surface. So rho will be that distance, which is, it says my inner diameter is 97 millimeters. So 97 divided by 2. I'm going to convert it to meters, so divide by 1,000. And we'll get 0.0485 meters. There's T rho. J, it is the exact same cross section as it was when we did part A over there on the right hand side. So it's the exact same polar moment of inertia. So I could just go and take this number and put it in over here, because that's what I calculated when I calculated the polar moment of inertia. Or I could put the whole equation in and do that, whichever. So let's see what number we get here. 22.5, that's kilonewtons, so times 1,000. Times 0.0485 divided by 0.1234 zeros, 347, and I get 31 point, let's do 45 megapascals. So the actual number is 31,448,126.8 newtons per meter squared, which is 1 Pascal newton per meter squared. And then I just converted it over to 31.45 million pascals. Let's see if WebWork agrees. Hopefully we will go back here. Yes, 31.44 is what we calculated, so that should be fine. I did 0.45, but I think it's fine. So this little part is for part B. Part C is the new stuff. So part C says, all right, if this is a hollow shaft just like it's described, what is the angle of twist from one end of the shaft to the other one? So it's 3.1 meters long for this hollow tube. We want to know how much does it twist from one end to the other if I put this 22,000 Newton meters torque on it. So let's go theta equals T L over JG. Same thing, anywhere in this whole 3.1 meters of shaft, the torque is the same. 22.5 kilonewton meters. The length, it gave me a specific length, 3.1 meters, so we'll just put that in. J is the same as it was when we were calculating the torsional shear stress, so we'll put that in. We'll put in the evaluated value. Now I am rounding somewhere in there, you know, 347, there was probably other decimals, so I won't get exactly the same number that WebWork has, but we'll get really close, I think. G, I don't know. So this is annealed titanium alloy. So we're going to need to go and find that material property. Where did our window go? Material properties. Yes, you're looking at it. All right, now this is one where you have to be careful because there are two exactly, well, not exactly, two similar charts with the same list of materials. One of them is US units. The other one is metric units. And yes, you could like just use one of them and convert to the other one, but the way these charts have been made, there's a lot of rounding in them. So you see all nice and even numbers here. So if I took the 48 KSI from this one and translated that over to pascals or megapascals for the metric one, I'm not going to get the same thing that's in the metric chart. So whenever you're working web work or exam problems, just go to the right chart. Don't try to convert between the charts. So we need this chart. And what was that stuff called? Titanium alloy annealed. Here it is. And we don't see our heading, so let's look over here. So modulus of rigidity, that's G. These charts don't have like the letter E or the letter G written on these. So if I were you, I would just write a big E over modulus of elasticity and a big G over the modulus of rigidity so that you know what you're doing. These are units of gigapascals, so that's billions of pascals. So it's this next to last column, and it looks like it is 36. That 36 right there. That's 36 times 10 to the 9th pascals. So let's put that in. G 36 times 10 to the 9th pascals. Now I expect anyway to get a really small number because we're talking about radians of twist, and radians are typically going to be small numbers anyway. 22.5, don't forget that that's kilonewton, so times 1,000 times 3.1. So there's my numerator. Let's go ahead and write that down. Oh, but that's Newton. There we go. My denominator I think I wrote it down right. 124,920. Those units are meters to the 4th times Pascal. Pascal is newtons per meter squared, so that's also Newton meters squared when I combine those, and those all cancel out because I'm going to be left with no units other than radian, which isn't really a unit like these. All right, so we might talk about radians in a second because I don't know that I have yet already. So once I get this number, we'll talk about radians. 69,750 divided by 124,920 is 0.558 radians. Let me check real quick if WebWork agrees with that. Oh wait, it wants it in degrees. So we need to convert our radians over to degrees for web work to be happy. So radians times, if I want degrees, I need 180 degrees in 2 pi radians. So multiply by 180, divide by 2 pi. That is not what WebWork said. So somewhere I have made an error. Let me see. Let me recalculate my numbers. Because it's not rounding, it's some other thing. And I could have typed something in wrong. I think the numerator's right. Oh, I better know what it is. This calculator won't let me put in the denominator the way I wanted it to. Alright, so let me redo that. 36 times 10 to the 9th times 0.0000347. Yeah. Oh, no, that's the... Oh, yeah. So I was off by a 0 here because when I was plugging in the numbers to my calculator for the 36 billion, I just typed 36 and then 9 zeros, and the calculator I was using, it didn't have enough space for all those zeros, so it just chopped them off, and that's why this number, I assume, yes, needs an extra 0 in front of that 5, and then multiply by 180 and divide by 2 pi. Oh, no, not 2 pi, just pi. I was thinking wrong. Just pi. 3.35 degrees. All right. So 180 degrees is 1 pi, not 2 pi. 2 pi would be the whole circle. Now, I guess you could do 360 over 2 pi, but I kind of put them together. So 3.35 degrees. I think WebWork's going to like that number. Let's look at it. So WebWork officially wants 3.2, and I have 3.35. I think where that's coming from is how I rounded this 347 number. I guess I could have typed something wrong in there somewhere. Let me just check that. And I rounded off the 0558. I rounded that off too. So if I do less rounding, I get 3.2. So I rounded here, and those two together gave me the 3.35. If you don't round those, you get 3.2, like WebWork wants. All right. Oh, I was going to talk about radians. So why we use radians? Because degrees make way more sense. Degrees are actually just completely arbitrary. The 360 degrees in a circle, that was just decided. Maybe the Persians, maybe if I'm thinking right, Persians did that. Maybe Babylonians, I don't remember. Somewhere in that area a long time ago, it was just decided that there would be 360 degrees in a circle. Actually, now that I'm thinking about it, it might not have been them, but it was just decided because I think they had a slightly different system. Anyway, that's not the point. 360 is a nice number because you can divide it evenly by a whole bunch of numbers. 12, 5, 2, 10, all these different numbers, 6, that can evenly divide into 360 and give you also a good bit of resolution. So you could just make 100 degrees in a circle and have a bunch of numbers you could divide by, but you lose some of your resolution of what 1 degree is. So 360 worked nicely. It also, 60 was an important number. Now that I'm trying to remember some of this stuff, That might have been Babylonians, where 60 was an important number, and 60 works with the 360 also. But radians actually mean something. They're a more fundamental thing. So here's what a radian is. So if we have a circle, and it has a radius, if I were to take that radius and map it to the arc length, so like this, so that red line, can you see? Yeah, you can see that. That red line is an arc length, and it equals whatever that radius was. So if the radius is 1 inch, then I drew a 1 inch arc on the circle. And if I connect, you know, these points here, this angle that is formed when I sweep that radius through that arc length, that's 1 radian. And so a radian is actually defined by the features of the circle. And so it has more meaning, and that's why a lot of times when you are calculating some fundamental type equation that has to do with angles, the thing that comes out of that equation, unless it has other coefficients in there that have been put in there that aren't really fundamental in nature but are, you know, they just convert it over to degrees, then the thing you normally get is a radian, because it actually has a relationship with the circle other than being a big number that's easy to divide by or divide into. So that's why a lot of these equations pop out radians instead of degrees. Now you will have some equations that pop out degrees, but they have something inside them that is converting the radians to degrees. That's just part of the equation in that case. And I can't even think of one of those equations right now for what the kind of stuff we're doing. But like we could just throw 180 over pi in front of this TL over JG and get degrees out instead of radians. So it's not really a fundamental equation at that point. It's just we put in a conversion factor so that we got degrees out of it. All right, so back to what we were doing. This other part's interesting. They want us to go in and do the same type of thing that we just did. So I guess I could maybe put a little box around this one. And that's part C. So for part D, what they want us to do is they want us to take the same amount of material. So this hollow, like we've got our hollow material here. They want us to take all of that same material, collapse it down to a solid shaft, and do the angle of twist calculation again under the same conditions, same torque, same length, all that kind of stuff. So in order to do that, we'll have to go in and, well, I guess there's a couple of ways we could do it. Let's just go and figure out what area this blue area is, and then use that area to create a solid circle. So the area of whatever shape that's called, but 2 concentric circles. Let's say this is the original area equals, let's use diameters. So pi d to the 4th over 4 minus pi, oh no, not pi, what am I doing? Pi d squared over 4 times pi lowercase d squared over 4. Those are the areas of the outer minus the area, not times, minus the area of the inner one should give us the cyan colored area that I've got in the picture here. So our numbers were pi, outer diameter was 145. I'm not going to worry with converting to meters for this. It'll be fine. Pi d squared over 4 minus pi, I think it was 97. So this will be the total area that we have. And then we'll just set that area equal to pi d squared over 4 and calculate that d. So let's see. 145 x squared times pi divided by 4. So 16,512.996 millimeters squared minus 97 squared times pi divided by 4. 7389.8 millimeters squared is equal to 16512.996 minus 7389.8. So our total area of our ring is 9,123 let's just do 2 millimeters squared. So we want that same amount of area, but we want it as a solid circle. So we'll do area solid equals 9,123.2 millimeters squared equals pi diameter solid over diameter squared over 4. And we can solve for the solid diameter. So let's multiply by 4, divide by pi, and then take the square root. Where's that? 107 point a bunch of sevens. Let's call it 8 millimeters. So if we had an equivalent as far as the amount of material, solid shaft, it would have 107.8 millimeter diameter. Whereas here we've got a larger 145 millimeter diameter, but it's hollow on the inside. So that number, we can calculate our angle of twist using that. So theta for a solid shaft equals, same torque is applied. It's the same length, different J though, because now we have a different cross section. So this one's solid, pi over 32 times 107.8. Actually, let's convert that to meters. So 0.1078 meters to the fourth. And then same material, so it did tell us to keep the same material, I'm pretty sure. Well, it says the same weight, but so we'll assume it's the same material. So G will be, what was it, 36 billion? Because that's the number I had trouble, yes. 36 times 10 to the 9th pascals. Okay, let's see. 36 times 10 to the 9th times 0.1078 to the 4th times pi divided by 32. Oh, I didn't put T and L in my equation. T is the same number, which was 22,500. Let me write down my denominator before I lose it. So the denominator here is 477,284.6. Those units end up being Newton meters squared. And my numerator, this T is 22.5 kilonewton meters, and L is 3.1 meters. So 22.5 times 1,000 to get it to Newton meters, times 3.1 to get to Newton meters squared. 69,750 Newton meters squared. Divide that by 477,284.6, and I get 0.146 radians. We'll convert that over, so multiply by 180 degrees in 1 pi radians, and I get 8.37 degrees. See if WebWork likes that number. Yeah, 8.38 and we have 8.373. So again, that's just rounding differences, but where I rounded some of these numbers. But here's the interesting thing. So 8.37 degrees. So we took the exact same amount of material that we had when it was hollow, but now it has a significantly higher angle of twist. 3.35 degrees when it was hollow. Same amount of material, hollow, larger diameter, but hollow on the inside. And the solid one has significantly more than double the angle of twist when it's the same amount of material but solid. So same weight, same everything else. Now there are other reasons why you might have solid versus hollow. Maybe there's space reasons, like geometry, it doesn't fit when it's hollow. There could be some frequency, like, so these shafts, we're not going to look at this in this class, but whenever you start spinning a shaft, there are certain speeds that it wants to spin at, certain RPM that could resonate with it and cause it to tear itself apart. Basically, it'll vibrate a lot, and so maybe we would want to avoid certain speeds or avoid certain frequencies, and the solid versus the hollow would have a different resonant frequency that one of them worked better than the other for what our application was. So there are reasons why you have solid versus hollow shafts, but it's not necessarily because of the angle of twist. The angle of twist is lower, which is normally what you want in the hollow version versus the solid version. The stress, I guess we could also check the stress. The problem doesn't ask us to, but we could check the stress here and see. We were getting our maximum shear stress was 47 megapascals. So for this one, 22.5 times 1,000 times our outer radius is, what was it, 107. So 0.1078 divided by 2, because that's the diameter, and then divided by our oh, I didn't calculate the polar moment of inertia separately. Let's see. Alright, so divided by pi over 32 times 0.1078 to the fourth. Alright, is that right? No, that's not right. I don't think. I'd have to write it out, because let me try it one other time here. So I think there's my denominator. Let's write it down. So tau, oops. Tau for the solid would be T rho over J. T would be 22,500 kilonewton meters. Rho would be the diameter over 2, so 0.1078 meters over 2. And J would be pi over 32, solid diameter, so I don't have an inner part to subtract off, which would be just 0.1078 meters to the fourth. All right, so I think my denominator is 0.401326 meters to the fourth, and my numerator is 22.5 times 1,000 times 0.1078 divided by 2, 12.75. Those units are Newton meters squared. So if I divide that by 0.00040 zeros, 1326, I think I get 91.46 megapascals. This is not part of what the problem was asking us to do, but just to see the difference in stress. Our max stress before was 47 megapascals, and here it looks like it's nearly double that. 91 megapascals if I plugged all my numbers in correctly. So that is one of the reasons why you might consider a hollow shaft versus a solid shaft of the same weight. So that's part D. All right, let's see. Let's look at web work real quick and see if there's any reason to do any of these other problems. Angle of twist is pretty straightforward. There's not a lot of let's see, maybe this one, we can skip the shear stress part, but maybe this one. Let's look at this. Because it has one thing that we haven't done yet. Okay, so we've got A, B, and C. For some reason they're in backwards order. And we've got 4 little bearings. So these little pieces here, that, and that, those are just bearings, like little roller bearings. They're not affecting our problem. In the real world, they would affect it some amount because they're not completely frictionless. And they do have to have alignment issues. But for our problem, they're just shown to make you aware that the shaft is not just floating in air. So this one's in US units, and we've got a 26,000 inch-pound torque supplied to the 3.6 factory drive, shown by a belt that drives pulley A. All right, so that's what I was looking for, is where is the torque applied? So the torque is applied on the right-hand side at A. So let's draw this over here. Whoops. So there will be C, and B is a little bit smaller, it looks like. And then A is the largest. Put it over here. Okay, and then there's a shaft that goes through all of these. Okay, and our applied torque, so the thing that's driving everything, oh, it looks like I'm a little crooked there, it's fine, is on this A. I'm going to draw I'll draw them as curved arrows, although sometimes you might see that the torque just shown like this, kind of like a force, but since we're looking dead on the side, then a circle would just look like a straight line. I will draw it as a circle like this. 26,000 inch-pounds. Then it says taken off, 21,000 inch-pounds taken off by the pulley at B. So we'll put that as an opposing direction. And 21,000, so most all of our torque is sent over to whatever is connected to B. And the remainder, so 5,000, is sent off to C. Shafts AB and BC are, okay, it gives us some dimensions here. So AB is this one. And for my units, or dimensions, it says 4.3 feet. So this is a big machine. And the other one is 2.7 feet. Both shafts are made of annealed red brass. So I don't know why you'd have red brass as this size, but that's what we have. And we're going to figure, we're not going to do the shear stress. We're going to do the angle of twist because that's the new thing. All right. So we would go in and pick one section. So let's do, just so we have it over here, this is A, B, and C. So we would cut open section AB and draw the left-hand side or the right-hand side. I'll draw the right-hand side because there's less to draw over there. Oh yeah, I have to do it all as one thing, don't I? There we go. You can make it really sloppy and it still figures it out. Okay, and so I put the 26,000 inch-pounds of input torque, and that means that in this little section right here, for this to be in equilibrium, I have to have 26,000 inch-pounds here. So section AB has 26,000 inch-pounds of torque applied internal to this section. Anywhere in there, that little blue section, I've got the 26,000 inch-pounds. And it wouldn't matter if I drew this version of the free body diagram or the other part, the left-hand side. It would still come out to be 26,000. Okay, angle of twist. Let's move this over here. Theta for AB equals the torque in AB times the length of AB. Polar moment of inertia is the same for the whole shaft, so I'll just use J. And G is the same for the whole shaft, so I'll just use G. It is possible that you have a section of the shaft that's got one cross section and another section it has a different one. We did one of those last time where it was a stepped shaft and it was larger in one section than it was in the other. So it is possible that the J does not stay the same for every section of the shaft. All right, so the torque we just found 26,000 inch-pounds. The length, this is the length. This is why I wrote AB on there. It's only the length of AB, so it's only the 4.3 feet. I will convert the feet over to inches, so 12 inches per foot. J, this one, oh, let's see, what does it say? Oh yes, it says right here, 3.6 inch diameter shaft. So it doesn't tell us anything about it, inner or hollow. So this whole thing is just 3.6, so it's pretty massive. So pi over 32 times 3.6 inches to the fourth. G, we're going to have to look that up. I don't know the modulus of rigidity for annealed red brass, so we're going to have to look that up. We have to use the right table. We don't want the megapascals now. We want the KSI. Red brass annealed. Looks like it's 5.6 over here. 5.6, those units are 1,000 KSI. So 5.6 times 10 to the 6th PSI. Almost under the picture there. There we go. All right, so let's calculate that. All right, the numerator, 26, oh, clear calculator, 26,000 inch-pounds times 4.3 times 12. So the numerator is 1,341,600. Those units end up being pound inch squares, whatever that is. Denominator, 3.6 to the fourth times pi divided by 32 times 5,600,000 PSI. 93,341,712.5 units here are also pound inch squared. And I get 1,341,600 divided by 93,341,712.5 is 0.0144 radians, or multiply times 180 divided by pi, 0.824 degrees. Let me just check if WebWork thinks that is correct or not. Let's see. So this would be part B, 0.832 0.8, we're close. We're in the same ballpark. Again, I rounded some, but we are similar. The other thing it wants is theta AC. So looking at my labels, AC is the change in twist from one end to the other end. So how we do this is the same way we did total change in length for axial deformation. You do one section at a time and then add up all of the sections. So we need to go over here and do BC, section BC. And I'm going to recommend drawing the same side of the free body diagram that we started with, because you can confuse yourself on if the torques are going in the same direction, the internal torques, if you work from both ends of the shaft. It's totally fine to do that. It's just you can easily confuse yourself on if these torques are the same direction or if they're opposite. So if we go from the same direction drawing our free body diagrams, then it'll be much clearer if we're adding torques or adding angle of twist or if we're subtracting. So let's draw section AB split where I drew that green line. So we would have, we'll move it over this way a little bit. So there's A. We would also have B somewhere over here. And then we would have the shaft that goes between them. And then there's a little bit sticking out over here. We would have our 26,000, that's a 6 inch pounds. That is not a 6. I've got it. So let's just rewrite that. 26,000 inch pounds. B had 21,000 going the opposite direction. So for this little diagram to be in equilibrium, the free body diagram, I need an internal torque here of 5,000 inch pounds, and looking at this, it is the same direction as the 26,000 internal torque from section AB, so it's going to have the same angle of twist. So we will get, I made this first one a positive angle of twist, so section BC will also be positive because the internal torques, this one and this one, are the same orientation. So they're going to add together. It's possible, you know, that depending on how the external torques are applied to this thing, it's possible that they could have the opposite sense and they would subtract. You know, one section is twisting one way and another section in the shaft is twisting a different way. That's not the case here, though. All right, so this is theta BC. So we need the torque in section BC, the length of section BC, and then J and G were constant for the whole shaft, so those can be the same numbers they were before. So the torque in BC is this positive because I made the 26,000 from the first set positive, and it's the same sense as that, so positive 5,000 inch pounds. That length is, I see it at the top of my screen, 2.7 feet. I'm going to convert 1 foot, or well, going to convert, not multiply, 12 inches per foot. And then the denominator is the exact same it was before, so I'll just write down the number that I had the first time. Okay. So here we get, let's see, 5,000 times 2.7 times 12 divided by 93341. 712.5 is really small number, 0.001736 radians, or times 180 divided by pi, 0.099 degrees. So the total theta A to C would equal theta A to B plus angle of twist from B to C equals, let's see, I don't know if it wants it in radians or degrees. It wants degrees. So 0.824 degrees plus 0.099 degrees equals 0.824, 0.923 degrees. WebWorks says 0.933. So we're off by a tiny bit, again, from rounding. It's not a calculation problem, it's just rounding problem. So that's how you would do the combined angle of twist. So you can't just try to figure out from A to C all at one time, because you have two different internal torques. The little blue section has a different internal torque from the yellow section. So you have to do them piecewise and add them together. All right. I think that is plenty enough angle of twist for today. So that's it for this week, actually. Monday we'll be back with more torsion stuff, but it's going to be power transmission. So we will actually be spinning the shafts and doing gears, pulleys, things like that, and transmitting power from one motor to some output or something like that. And all the while calculating torsional shear stress and angle of twist in our shaft